One a day is...
It's on. It's on.
All right, let's do this. So welcome, everyone. Today we're going to do a brief. Keyword there is
introduction.
That's right, because I'm no expert on the topic. I have to preface the conversation by saying that, but I do know a little bit. And you figure, heck, in an hour, hour and a half, how much can we do anyway? So we'll do an introduction to mathematical induction. My name's Dave. For those of you that don't know me, nice to see you. There you go. So here's what we're going to do. All right, we even have some goals. Use it loosely. But the idea is, of course, we want to become familiar, at least this basic idea, what is mathematical induction, how is it used, when is it applicable, some stuff like that. We're going to talk about the steps that are used to build an inductive proof, and it's basically the same set of steps that apply to different problem situations. And then I've got a bunch of examples for us to work on. That's where the fun really comes in. Yep, there you go. We'll talk about triangular numbers, some counting arguments. It's more summation stuff. So how many of you, a bunch of you I know are in 253, right? Yes? No? Tom is, right? Okay. Well, there you go. 252, 250. Well, anyway, you count stuff in math. You count stuff. Yeah. That's how it's going to work. Some good examples about divisibility, some examples that involve inequalities, and there's an inequality that you had last time, which says 2 to the n is greater than n. For all n, and well, heck, we can't prove for all n, but we can certainly prove it using induction for natural numbers. So we're going to play around with that a little bit. That's our inequality example. And then there are actually a couple of results from differential calculus where we can apply this concept of induction to prove. How many of you have ever used the power rule? Who passed your 251? You ever prove it? Even for like whole values of n? Today, well, now we'll have the right to use the power rule for x to the n where n is a positive integer. And we can actually generalize a product rule. So we'll see if we get that far. It'll be pretty awesome. You'll see. Don't want to oversell that one. All right, so the basic idea, we'll start here. And one of the ways you can think about a proof by induction, or this concept of mathematical induction, is it's kind of like dominoes. And if you suppose we have an infinitely long row of dominoes, and you can see it from back here, right? It's a big enough font. And they're, well, yeah, they're standing on end. If a domino falls, then the next one's going to fall. That's sort of what we have. Everyone's played, done that with dominoes before. Makes reasonable sense. So, of course, what are we assuming here?
Gravity.
Sure. I live in a world with gravity, but I'm assuming that we didn't set them up horribly, right? But if the fifth domino falls, what necessarily has to happen according to that statement? The sixth one falls. If the 75th one falls, then the 76th one falls. So it's that type of idea. So here's the big question. What happens?
They're set up right, all of them.
They're all set up. They're perfect, Tom.
They should all fall.
Yeah. They have to all fall. Because what does the first one do?
Knock the second one out.
Knocks over the second. What's the second one do? Knocks over the third, so on and so forth. Until what do we have? An infinitely long row of dominoes that are all knocked over, which is kind of cool. That will get us on the YouTube channel. All right, so of course, there you go. It's inevitable that all of those dominoes will fall so long as what's true? Each one knocks over the next. And if that happens, we're in great shape. So there you go. That's the basic idea. So we can make it a little more formal for our purposes. And before we do that, let's talk about the natural numbers. What are the natural numbers? Counting numbers. What are the counting numbers? Someone said that.
1, 2, 3.
1, 2, 3, so on and so forth. Right? So we often think of them as the positive integer values. Right? But we need... Right, that's the set of natural numbers. And what we're going to do is we're going to work with statements that are indexed on natural numbers. So if we know that a statement is true for some starting value, what's our starting value? It's the first domino we push. Right? And if we can show that if the 75th falls, that the 76th must fall, then we've got our proof. That's really what we're saying here. But of course, we're not saying the 75th knocks over the 76th. we're going to say that the kth statement forces the next statement. What would the next statement be after k?
K plus 1.
Yeah, the k plus first statement. Boom, then they all have to happen. We push the first domino, and each domino knocks over the next is the basic idea. And of course, that gives us a statement that has to be true for all values. All values of what? Right, natural numbers. So we're living in a world without fraction or negatives, which is kind of cool when you think about it. Makes everything so much easier. All right, so let's make this a little more formal. So for each natural number n, we'll let p of n, and quite often this is like if you Google the mathematical induction, half the time you'll see it written in something resembling a function notation, the other half of the time you'll see it with subscripts. So it might say p sub 1, right, or p sub n. But the idea is that we have this statement, p of n, which is a statement depending on our natural value n. Now, if the statement p1 is true, meaning
The dominant.
we push the first one. And if we can show that the kth domino forces the k plus first domino, then it must be true for every natural number. So that's sort of the formal, slightly more formal framework for an inductive proof. So far so good. Questions, comments, sharing? The only thing I know is about dominoes, so I'll keep saying it again and again. All right, so turns out this proof technique sort of follows a very standard format, and I'll just block that for you. 3 parts. First, we're going to need our statement that we're going to prove. If you're going to prove something, you ought to know what it is. Right? Basic idea. Everyone's comfortable with that? Good. Here we go. Second piece to this, and we'll keep this on the board so we have it for later. Right, is referred to as an anchor step. It's often referred to as a base case. So what's this? Something that shows we're pushing over the first domino. And then the second part of this proof is called the inductive step. And that's where we show if the implication p sub k implies p sub k plus 1 holds for all the k, then it works. Right, so there's our framework. Questions, comments, sharing? And there's sort of 2 pieces to the inductive step, which we'll get to in a second here with an example. So this one's kind of cool. Found that on the Google machine, but it didn't copy that well. But that's all right, because I've got another variation of it. So what we're talking about here are called triangular numbers. All right, so give you a second to read the definition. Enough reading time? Josh, you made it? You're a slow reader, so we know we're good. All right, so what we've got, these numbers called triangular numbers, and there are other numbers called like square. You know, there are other types of numbers that are defined similarly. It's kind of cool. But it's the number of dots in an equilateral triangle evenly filled with dots. For example, 3 dots can be arranged in a triangle. Right? There you go. A triangle, thus 3 is a triangular number. The nth triangular number is the number of dots in a triangle with n dots on a side. So, first, what would we call this?
First triangular number.
Yeah, not a very interesting triangle, right? Certainly, it's not that interesting. But we would call that... Anyone see what I did with my pens?
Where are your bags?
No, I put some out.
There's some right here.
I'm certain of it. No, but they're somewhere, John, and
Look for them.
left hand.
It's brutal.
Kind of cool, isn't it? All right, so the first triangular number is 1. It's pretty funny. The second triangular number would be, right, 3 dots required to make the equilateral triangle, so that's kind of cool.
Are they all multiples of 3?
Oh, let's find out.
That's a good question.
Count them. How many do we have there?
6.
1, 2, 3, 4, 5, 6. Oh, that's kind of